Будь здоров.
Спасибо.
Так, еще кого-то я зачем-то поставил, что я должен здесь вот это admit нажимать каждый раз. Ну ладно. Okay, so let's let's come to the lecture. So last time we discussed once again the card geometry. I also made some references to François Villette, his treatise on algebra. And actually, central thing was distinction between analysis and synthesis, which I think it's really, really important for understanding developments of late 17th century, early 18th century. And actually a major event of that time, if you open any general textbook on history and mathematics, will be discovering of integral and differential calculus, and which is, of course, championed by Isaac Newton and Gottfried Leibniz. And actually, that was actually a later story started by their pupils rather than this honorable two men themselves. Was a contest about priority, who invented first, who invented what, because it was so much a success, which actually was not only in pure mathematics, but was at least equally important in physics. I mean, publication of Principia, principle of mathematical principles of natural philosophy by Isaac Newton. So I think we begin very briefly of kind of overview of these developments. Then I want to say something more. That's just something I spent some time researching recently myself on Leibniz project, which calls analysis situs. And in many, again, textbook or even more popular presentation of history, this is referred as a kind of prototype of what later became topology, which is actually at least requires a lot of reservations that I also will try to make. I think that that's, in a sense, it's still a project. I think it's inspired many people during, say, 18th and 19th centuries, and I think it still remains inspiring. Even by itself, it was not accomplished project at all. All right, so I will mention this, and then I think we need again to focus on philosophy. I'm trying not to, how say, to combine these things, history and philosophy, in this course. And of course, many things we discuss in history, such as analysis versus synthesis, for example, you may qualify them as philosophical topics, broadly speaking. However, still there is some, how say, I should make an effort to switch from history of mathematics to philosophy of mathematics and back. And I think it's very important piece of philosophy historically that we cannot go through, which still remains very important and widely read. I mean, Immanuel Kant's works. No, we actually we don't have much time, so I think we focus only on one work and actually on some particular aspects and fragments of this work, which is probably you heard about, Critique of Pure Reason. So that's, I hope, also have time to do today. So you see, there are many things. Let's probably start with this discussion with Newton. Sorry, I try to share my screen, and yeah, so that's my first reference today. It's his treatise on method of fluxions. I think I mentioned it already also last week, but let me say a little bit more about this. So this is actually a book composed by Isaac Newton in 1671, but you see it's published officially more than a century later. It's rather also interesting, and I think somehow important. So that's of course the beginning, what we call today in Russian mathematiический анализ. The same term analysis actually is used in French. In English, it's more usually referred as calculus, right? Even without specifying what kind of calculus. And of course, this is a specific calculus, because calculus is a broader term, which is also very, how say, much in use these later years because of rising of computers, of general attention to computational aspects of mathematics. But here we talk about specific calculus related to infinitesimals. Do you all know term infinitesimal in English? Yeah, infinitesimal is what refers to infinitely small. And actually, it's also interesting that, say, with the rise with counter set theory, we somehow know a rigorous way to talk about infinitely big, right? But still, sorry?
Бесконечно малое?
Бесконечно малое, да. Infinitesimal. That's a term for, it's not specifically English term. It's so somehow it didn't go to Russian for some reason, but it refers to infinitely small. Exactly. So today we also have some approaches to infinitely small. I mean, official, rigorous, according to today's standard, with the so-called non-standard analysis that probably some of you somehow championed by Robinson first, and later developed by some other people. However, there is this, how to say, asymmetry between axiomatically big, infinitely big and infinitely small that was brought by, say, set theory, because say again in set theory somehow it justifies the idea of infinitely big, but not idea of infinitely small. And so here we come to some other ways of justification, including this non-standard analysis, which on the other hand, as far as I can see, remains rather isolated. So we somehow know how to justify these things via non-standard analysis. On the other hand, it's not something which is generally used, and I think in courses on integral and differential calculus, we still stick to kind of 19th century foundations of Cauchy and Weierstrass. There is also another more modern way to put it in some ground, say Bourbaki style infinite analysis by Schwarz. I don't know, how do you study it these days? This integral and differential calculus, it's a question. So it's it's still more like Cauchy, Weierstrass, epsilon delta technique, right?
I didn't study here in bachelor, but I studied it like classical calculus.
But what do you mean, classical?
I mean like Cauchy and Weierstrass.
Yeah. So that's 19th century way, which is, of course, quite justified. But I think there is a really, how say, interesting theoretical topic, because on the one hand, it's of course historical topic. So the usual general narrative is that these people like Newton and Leibniz, and then a lot of their followers already in 18th and 19th centuries, they developed this analysis without firm foundations, as it's very often evaluated and qualified. And then people like Cauchy and Weierstrass, they developed new technique for making that's calculus, right, and reasoning with this calculus more rigorous. Yes. However, I still think that there is something even theoretically interesting, say, today, right? Because this 19th century stuff, also in 20th century with, say, Hilbert, axiomatic method, say, set theory already, I mean, axiomatic set theory in 20th century somehow was evaluated as not fully rigorous. Maybe it was just sufficiently rigorous for say, teaching, for studying, but if we want to really, I would say, develop foundations, then we should do something else, like non-standard analysis, amongst other things, right? And I think here there is something still, how to say, probably to be developed. No, okay, I'll maybe try explain this later. I don't have very clear picture and project in mind, rather some ideas that I'll try to share. So what happened with Newton? And I think that this history, it just was saying there is a history, right? But there is also a theoretical ideas which I think are still interesting. So it's not kind of closed topic. So he developed this method of fluxion, which is rather messy. If you look, the text is available. I think I still didn't put it, I'm sorry, to this folder, but I'll do, I promise. So there's a lot about infinite series. Fluxion means roughly derivative. So he develops this vision. I would use exactly this word, vision, because it's not really a theory. It's not even a concept. Say of we may say continually variable magnitude, right? So roughly, he uses variables, but his understanding of variables is rather special, right? So those are variables not in a logical, not even in today logical sense of the term, where you have symbol and you imagine that you substitute it with, say, certain values, right? So he rather thought, just think about continuous function, right? And Newton would think about every variable basically as continuous function of some parameter, which he would think of as time. Okay, so it's kind of very different and unusual for anything classical mathematical universe. So there's continuously changing magnitudes. Okay, which he called fluents, which is just in Latin means something that is a flow, something that changes continuously. Continuously is important, of course, that it changes continuously, and that made a lot of, how say, it's related to, say, certain non-continuous things and many further developments. Fluxia are what we would call today derivatives, and there are continuous series. There is no concept of limit in, say, that's modern sense, which is actually 19th century sense, more or less. However, there is a lot of these reasonings, and this whole book or booklet is actually about problem solving, right? It's not a theory, right? It's not. It does not develop from any sort of first principles, and indeed that's corresponds to its title, because you see this word method in a title, and method is a method, right? And the close concept to that of method is that of analysis. And as I stressed last week, analysis is supposed to be some sort of heuristic procedure. It's simply not supposed to be a part of theory, right? Which is synthesis. Remember this, recall this Pappus way of distinguishing between analysis and synthesis, which we may believe is very traditional and comes and goes back to some Greek geometers. Okay, so actually the fact that he did not publish that book, right, and somehow only shared some stuff with his students and so forth, or probably something just kept to himself, it's not just a, how to say, historical contingency, right? It just related to that fact that you are supposed to publish a theory, something where you state theorems, or probably you solve problems, but important that you justify everything, right? And method, actually, it's it's not immediate, at least, right? That method should justify anything, right? So you may think about method as just as a kind of useful trick you are doing, but after you did this trick, you should somehow justify that what you did was right. So that may be compared with, say, solving algebraic equations. Because once again, when you solve equations, you use certain methods. However, if you stick to this traditional scheme of analysis and synthesis, then a proof is actually a checking, right? What you obtain by whichever method you mean, but you obtain something, solution, right? And then you should verify your solution. That's verification of your solution is actually proof, right? So that's according to that standard, only that deserves to be published, right? To be somehow put on the judgment of other people, of public, and your method you may just keep for yourself. And by the way, something similar we find, say, in Archimedes. Some of you, I don't know, it's who is going to write a work on Archimedes? Not among people in the audience, not? Okay. Because only in one available work of Archimedes, which also has this method in its title, he actually kind of reveals how he solves his problems, how he proves his theorems. I mean, how he finds proofs of his theorems, right? While the most of his work simply keep this absolutely hidden. And by the way, and probably less surprisingly than it may first appears first, in Archimedes, we find something very close to this infinitesimal reasoning, to calculus, and that gives reason to talk about Archimedes somehow going ahead of his time and so forth. And that's true in a sense, but I think it should be also kept very firmly in mind that it's also a question of epistemic standards. You see, what really qualifies as a piece of mathematics as a kind of public piece, right, of mathematics, as a justified mathematics, and what counts as just somehow a bunch of methods, of tricks, which probably does not deserve publishing. At least that was Isaac Newton's decision, right? So he quite deliberately did not publish that work during his lifetime. He shared some of that knowledge, something he shared with Leibniz, with other people in letters, and probably just orally, otherwise. I think that is very well researched. I'm not, I should say, expert in Newton. However, of course, all his writings were researched very, very well. There is a huge literature on Newton of very high quality. So I rather want to emphasize this epistemic aspect, which I personally think is really interesting and really important. What he did instead, he published later, and exactly in 1687, first version in Latin. Later he made kind of authorized translation into English. So he published that work, which is absolutely different. There is no fluents and fluxions, we call them, in this work. And actually, I think even if this is probably one of the most famous work compared with Euclid's, for example, in all history of mathematics, which really had the greatest success as ever, I think. No, it's more difficult to compare with Euclid, which is very old, right? So it's very, very different society. But Newton is still closer. So it's, of course, the life changed since 17th century, but not that much as from Euclid's time, certainly. So again, what is usually said that he followed Euclid's example, and that's well evidence that, of course, he did have Euclid's elements in mind when he composed that work, and it's indeed it's synthetic, right? However, of course, it's not based on Euclid. There are principles which you don't find in Euclid, of course. And again, I actually don't see much of literature which analyzes this very well-known and researched book, say, from logical point of view. There are some modern reconstructions. By the way, one recent reconstruction I found was made by a computer scientist who just was not professional historian, but just made, but very, I think, attentive, actually, work. Right. However, usually it's qualified, say, as traditional, and it's often again said that actually what Newton did, right, that he had some really new vision, say, exposed in particular in his book on fluxions and in some other mathematical papers that we know, which he didn't want for some purely, say, social reasons to show to public, and instead he did something more traditional. So he found a way to represent all his results in a more traditional way. And that's, I think it's true. And by the way, that was, socially speaking, was, we may say, a posteriori, a right decision, right? Because the success he got, and that sort of recognition he got, was made in that way. So we don't know what would happen if he published first his method of fluxions. However, I think at least this is not whole truth, right? Because there were some, I would say, serious reasons to do that. And the serious reason, which is rather obvious, is exactly this, that he simply considered methods to be, as many other people, his readers, as something which does not really deserve publishing, right? It's not a firm theoretical result, it's just a method. Probably deserves be shared with pupils, but not published as a, say, official result, official theoretical book. And I think that that's very interesting controversy, because recall also what I said about Descartes, right? And his philosophy of method, his geometry, because Descartes had this idea that, roughly speaking, we can get rid of synthesis after all, right? That if we do this analysis or methods in a certain way, then it may turn out that it becomes kind of self-justificatory, so to speak, right? So we may probably get rid of this traditional scheme that we should first find something, right, by some heuristics, some sort of calculus, and then restructure this in that more traditional way, where we distinguish first principles and we deduce the rest as theorems. And in a sense, this, many people, probably even without reading Descartes, without being Cartesians, they followed that way, indeed, right? And they were really successful. No, I mean, people like Euler, for example, right? Who, by the way, wrote the first really textbook on mathematical analysis in the sense of differential calculus. So he was the first. It was very revolutionary in a sense, right? So it was certainly more systematic. No, it is, by the way, it is also available now, of course. It is more systematic than these early works, including Newton's. However, it does not follow this Euclid's. It does not stick to Euclid's standards, right? And why I think that it's something to be thought about even in today's context, because say with the development of say what we usually call modern axiomatic methods, right? Modern logic. So we now already talk about 20th century mathematics, in foundational mathematics in say current sense, or 20th century sense at least, right? Then in a sense we came back to this traditional idea. So we changed our logic, right? Of course, the most important figure historically here is probably Gottlob Frege, who made some sort of revolution in mathematical logic, which is still important. So kind of thing that you probably study today in mathematical logic courses, like propositional calculus, first order predicate calculus and stuff. That's all depends, say, on Frege's discoveries. So we really made a lot of advances. However, in a sense, the standard scheme was restored, right? So the modern axiomatic method, even if it's rather unlike, say, Euclid's, in many respects, I hope we'll talk about it in maybe a couple of weeks from now, it's still axiomatic method, right? So it's still there is the idea that we lay out axioms and derive certain theorems from axioms. So by these old standards, it's of course all synthetic rather than analytic, right? And by the way, maybe you heard about this name of being synthetic was kind of popularized by people who developed category theory and who try to think about category theory as a kind of new foundation of mathematics alternative to set theory. And actually what they had in mind mostly, they had in mind the idea that you might develop something like analytic geometry, but not in the analytic way, right? Without coordinates and from some kind of new first principles related to category theory, right? And I think these people, and that became a rather popular word, synthetic geometry, for example. If you Google, you find many stuff. I think it comes from Bill Lovier specifically, even I'm not absolutely sure. There is for example, discipline you may Google for synthetic differential geometry, which was a project motivated and probably initiated even exactly by Bill Lovier in say late 60s or the 70s, but then developed by one of his collaborators and in a sense followers, Andreas Koch in Denmark. I can show you synthetic geometry. Yeah, so what I want to say that's sort of interplay between analysis and synthesis. I believe it remains a very vivid topic. Okay, so and really to understand what is going here, I think we should really go back to history, which is I should say is rarely done in works like Lovier or Koch. You see them here, right? So that's outline, geometry. No, that's already later, but I think that comes back to his ideas, which were somehow conceived back in at least 70s. So you may look into that stuff. I think it's very, very interesting. However, at least my experience that people often simply don't go that back into history, which in a sense is justified why they should go to history. But that's, I think, what you really need to understand what is analysis and what is synthesis in the relevant sense of the term. Because people often simply associate idea of being analytic, at least in geometrical context, with, say, coordinates, right? Because everybody learns analytic geometry these days in this form. And that, I think, is just wrong, because however coordinate could be important, the somehow essence, the main content of being analytic, and why that geometry is still called analytic is not because of coordinates, not certainly because the idea that you somehow translate geometry into arithmetic, certainly not. That only came to but because of that stuff that I try to explain to you, right? Just that different of analysis and synthesis that say is described in Proclus and some other sources. Yeah. I don't want to use that for some reason. Okay. Okay. So I think no, I think I will not try to somehow overview these works, which of course huge and very important, and have some. No, probably I should say some general things, say about Newton's Principia, that he derives their Kepler laws. Probably you know about. Do you know about Kepler laws? Is it?
Yes.
Oh, okay. Yeah. So he derives them. No, again, modernizing, we could say he solved differential equations and find these laws, which were empirically. No, I think that needs some also reservation that Wikipedia says Kepler had first obtained these laws empirically. No, I think that some reservations needs to be done, because indeed Kepler used the data, observational data by astronomer Tycho Brahe, which was the best available in his time. That's true. However, say these data were actually compatible with the idea that all planets moves in circles, not in ellipses. So there are actually two factors. For one thing, Kepler followed Copernicus, right? So he defended this Copernican system. So unlike Ptolemy and say Tycho Brahe himself, for example, right, who still stick to Ptolemy in that sense, he tried to use this heliocentric scheme. Even if mathematically speaking, I already stressed that, right? You may, using this epicycle techniques, you may describe mathematically the observed motions of planets with any degree of precision. So it's not a mathematical demand, right? So there were no, say, empirical observation which would say that, say, Copernicus was right rather than Ptolemy. So it was related to many other things. And even immediately, it didn't give mathematical advantage, right? By the way, this probably you heard about this theory of Galileo, right? And the Papus Urbino, if I not confuse his name, that Galileo was condemned for defending this view, the Copernicus view, that the Earth is in motion. And actually, what this Papus, what he insisted upon, right? It's just for saying that motion is relative, right? There is no physical or kind of realistic assumption behind that. So if for some mathematical reason you may either say phenomena by assuming the Earth being immovable, okay, so go ahead. The church had nothing against that, right? But the church was against the realistic claim, the claim which really pertains to truth in a serious sense of the word, right? That Earth moves, right? No, that, you know the story. He accepted. Then the legend has it that he still believed that the Earth moves. So it was not empirical question of the choice between these two systems. However, was an interesting detail. So Kepler, just sticking to heliocentric model, right? He could still use circles instead of ellipses. However, in that case, right, he had to, I would say, to place the center of motions of planets not in the center of sun, but a little bit apart of sun. So roughly speaking, you may approximate the observed to that time, right, by Tycho Brahe, observed motion of planet by a circle as well as by ellipse with roughly the same degree of precision. However, in order to do that, you would need to move center of your circle a little bit off the sun. It's clear, right? Right. And that's something Kepler didn't want to accept, because it's he was also thinking very, how to say, realistically about these things, and that's just seemed to him very unnatural thing to do, right? Why or not? So he really probably the first here. I'm not so knowledgeable in that history of physics, but probably he was the first who really conceived of something like gravitational force. Even he could not yet describe it as nicely as later did Newton. Still he believed that there is gravitational force which makes all this planet move, or at least somehow determines all these motions. And that's why, so he would like to think about sun as, in a sense, a cause, in a physical sense, right, of these planetary motions. And that's why he didn't want to displace the center of these motions somewhere. And that's how he found a different mathematical solution using ellipses and putting sun exactly in one focus of corresponding, or one of the two focuses of the corresponding ellipse for each planet. All right. So, now, of course, Newton managed to put all that in a system, and what we learn now in school as Newton's laws, right, which indeed are principles of his physics and principles which are formulated mathematically. I think it's also kind of characteristic that he calls his work mathematical principles of natural philosophy, right? It's not simply principle. By the way, there were also in Newton times interesting discussion on whether or not physics should be mathematical. No, actually, it's a very old question. We find also interesting discussion of that sort in.
Sorry, which year is it?
No, now we are talking about late 17th, early 18th century. But the very question, of course, on, say, relationships between mathematics and physics, I think it's still very vivid, of course, even today. However, it certainly goes back to Aristotle. We find a lot of stuff in Aristotle on it. And remember that Aristotle actually invented at least the term physics, physica. Actually, it's almost in Greek, like in Russian. Basically, he used this suffix K, like physica, dialectica, and so on, just to denote, say, discipline. Or perhaps it did some of his students. That's of course we don't know whether it was Aristotle himself or someone of, say, his students who wrote down his lectures. Probably not himself. That's we never know. However, he actually insisted that physics does not reduce to mathematics, roughly, which was basically Platonic view, right? Because remember, in Platonic view, like the best science, save philosophy, save dialectic, right, is arithmetic, not just mathematics, arithmetic. It's kind of purest, right? And then comes geometry. And then, only then, comes astronomy and harmonics, like theory of music, right? So the idea here that we have kind of pure science of arithmetic, which is the best in terms of its epistemic qualities, like rigor, like simplicity in a sense. And next best is geometry, because you know that's say Platonic definition of a point. It's not in Euclid, but Aristotle quotes it in his Physics, that a point is a unit, like monas, right? Monada, which has a position, so it's kind of placed unit, right? And this quality of being placed, it's according at least to some reasonable, I think, interpretation of Plato's views, is kind of distortion, right? So it becomes less pure than it was a unit, right? When it becomes a geometrical point, and then there is certain complexity, and only then there is kind of hierarchy here, right? From arithmetic to geometry, and then to say astronomy, where we have not only this imaginary position, I wouldn't say space, because there is no notion of space in Greek mathematics, even it is in Plato's philosophy, by the way, right? No, anyway, space is still something intellectual. However, in astronomy, we have to do not just with the intellectual space, but you have to do already with observable space. However, it's still a heaven, right? So we can do mathematics on the heaven. However, if we come back to our Earth, then it's total mess, and we cannot do anything, almost. That's roughly, maybe simply, by the way, this partition of mathematics, but mathematics in this broad sense, which that time actually includes roughly all science. Arithmetic, geometry, music, and music, theory of music, and astronomy, right? So that's what was called later quadrivium, and studied in medieval universities. So Aristotle changes that vision, right? So he claims that actually astronomy is the best science. And this is because he somehow does not qualify that kind of hierarchy as, how say, as the most important. So he kind of recognizes it, but he says something of the sort that it's kind of theoretical hierarchy, right? That does not really refer to reality. So for him, what we observe is, after all, more real than what we just think about as, say, numbers, right? And then he has all this theory of abstraction.
Sorry, he said, who said this?
Aristotle. No. Sorry, I'm jumping between different. No, that's about Aristotle. I just want to say that that's a story about how mathematics relates to physics has this long theory, long history, which comes back certainly to Aristotle, who in a sense is inventor of physics. If we understand physics more, say, narrowly, then we may say Aristotle is one who invented this discipline. Certainly he, or say his students or someone, invented the name. So, right. And then Aristotle insisted actually that mathematics is not reduced to physics. Physics is not reduced to mathematics. And of course, physics for him also meant biology, say, all natural science. So his kind of motivation came from medicine, from thinking about animals. So physics, you should also, if you read Aristotle's physics, for example, and just if we are talking about this ancient concept of physics, it's all natural science. There is no difference between, say, physics and biology, and moreover, chemistry for that time. Okay, so that's all. Sorry, but I mentioned that that idea of making physics mathematical also was still controversial, at least in certain circles. Actually, certainly for Galileo, also, right, where roughly in his dialogues there is different characters, one of which, say, represents Platonic point of view and other represent more traditional for that time Aristotelian point of view. And Galileo himself, he pursues what he think of as a Platonic point of view, see? So that's insistence on importance on mathematics in physics, that's actually looked Platonic. And I don't know, probably would not be quite justified to call Newton Platonic and find some connect, but historically there is certainly a connection here. By the way, another important how to say player in this controversy, say, between mathematics and physics is logic, because for Aristotle, what was the basic tool of physics was not mathematics but logic. That's also important, right? And of course, development of this new physics with Galileo, later Kepler and Newton. By the way, René Descartes also had his project in physics, which, unlike his mathematical project, we could say completely failed. That's also interesting, but okay, I don't have time to talk about this.
Sorry, and for the full picture, what Aristotle thought about primality of mathematics and physics, between mathematics and physics?
Yeah, that's a good question. No, I would say that physics as such is autonomous for Aristotle. So he kind of recognizes importance of mathematics in physics, talking about, say, astronomy, because for him it's also kind of physics, right? However, he insists that there are principles in physics which are not mathematical, right? He even says in his metaphysics, he says things, no, at least as I read it, he describes kind of trade-off, so kind of balance between mathematics and physics, and saying things like mathematics gives us advantage, say, of rigor, right, of being precise, while physics gives us advantage of talking about reality. I would say something like that, right? Or in a sense, physics is about real things, and in a sense that's view which became very basic. I think we very much inherit from Aristotle still, even if we many people, and rightly, discover this so-called modern revolution made in physics, and indeed it was kind of revolution of people like Galileo, right? Because physics really makes a new start at that time, right? If you take physics by Aristotle, it's not physics. I mean, in today's sense, say if you take Newton's book, it is physics in today's sense, and not Aristotle. Yeah, but still, I think we inherited a lot. And even this very basic idea that I know that there are different views, right? Some people promote kind of mathematical Pythagoreanism, that mathematical objects are real and only real. However, that's kind of commonsensical understanding that physics physics treats reality somehow, right? And experience perception is just very important part of it. It comes from Aristotle. It comes from Aristotle. So in works like Newton's Principia, if you like, there is kind of great synthesis, right? So a large part of this Principia, even it has this name of mathematics in its title. Actually, it treats a lot of data. So he applies his laws to observations and finds and look for, how to say, for adequacy, that his mathematical principle really describe what is observed astronomically, first of all, but not only astronomical, right? Because, of course, a very important part of this revolution, which actually somehow makes a difference between Aristotle and, say, Galileo, was the abundance of this idea of that heavens somehow are different in nature from what we find on the earth, right? Which was part of Aristotle's thinking, of course. All right. So according to Aristotle, we're a kind of sublunar world and heavens. And if you think it looks like kind of crazy metaphysical idea, however, in a sense, this idea is very well confirmed by observations, right? Because indeed, the only situation in in our experience where without making some special technical stuff, right, technical experiments, we find something which is regular, right, and exactly because of that reason can be described mathematically, is astronomy, right? What regular we find on Earth. No, so we also find something regular, like, say, seasons, but that clearly depends on astronomy, right? There are changing seasons exactly because it has, say, astronomical explanations, which were obtained very early. So that idea that physics on the Earth is just very unlike physics on heaven, it comes not only from some, say, metaphysical prejudges, but it comes from observations, kind of long-term observation. And still, it was, of course, very important part of this 17th century revolution that people somehow abandoned this idea. No, actually, they abandoned through kind of important. It's a little bit off of our topic, but I think it's important since we are talking about Newton, of course, right? And that was related to idea of experiment, right? Not just think about, I think it's first Newton's law, right? If you have a body which doesn't experience any external force, so it continues to move in inertial frame and continues to move uniformly, right? You can't observe it, right? Immediately, it never happens. By the way, Aristotle had different theory about this. His theory was that so he had a problem if you throw, say, a stone, right? Okay, then the kind of first analysis is rather clear. It's your hand, your muscle, which is a cause which makes the stone move. Okay, that's clear. But what happens if stone kind of leaves your hand and continues to move? So Aristotle had a problem with that. So he looked for explanation. And actually, he explained that by some motion of air. So he imagined it would be kind of a vortex in the air, which makes this, say, stone or whatever, ball to move even when you no longer push it. You see, which of course was completely wrong as we know. He couldn't check it, so he would need make some sort of vacuum, right, and see that in vacuum it still goes, it still continues to move. So what I want to say that somehow to formulate such a principle as physical principle, right? It's you need a lot of abstraction, right? It's not what you can observe, but what you can do, and exactly what Galileo did, you can kind of approximate that situation, right? Say if there is no friction, and you can kind of approximate no friction by, I don't know, polishing or whatever. So you are making some like experiments to reveal the truth. So it's very different idea about, say, physics. And the idea is actually, we are coming close to Immanuel Kant now, because Immanuel Kant somewhere says that we need kind of violence to torture. I think he didn't use word torture. It's my word here, to make nature to reveal its secrets, you see? And that's what we do using, I don't know, Large Hadron Collider, or even simple things that Galileo did, you see? But important that we do something which does not happen naturally, you see? Say for Aristotle, that would be contradictory, right? If you talking about nature, you should pay attention to what is natural, right? You shouldn't force anything. And here it's a very different notion, and which of course relate to mathematics, relate to the fact that okay, we cannot obtain ideal mathematical plane. However, if we approximate it somehow, right, we see that the body moves along that plane, and that, by the way, also provides that kind of join between mathematics and physics. So you see, and very different kind of join than we find in Ptolemy. So the idea is that we're not simply saving phenomena, right, using Ptolemy's word, not just making something mathematical that looks like observable, right? No, we kind of insert mathematics in the core of physics, you see, and then say what we observe is, if it's not so mathematical as we really imagine, that's just a problem of, say, kind of human incapacity to polish your plane ideally. And that's very, very different way of thinking about these matters, which kind of championed in this work by Newton, of course, right? That's indeed, it's allowed to do what looked like really marvels, right? Like discovery of new planets just by calculating observed perturbations of motions of other planets, and so on. All right. But actually, I made all that long speech because I just remembered. No, first thing for saying that the issue whether or not physics should be mathematical, it was still discussed, and no, at least this very issue of say relationship between mathematics and physics, I think it remains even important today, and in context of today's physics and mathematics. No, just give you example, something I'm not really expert, but probably some of you read the books of Lee Smolin. I don't know, it was who was a string theorist, but later he somehow converted himself against string theory. And so at least his critiques of string theory is that it's too mathematical in the sense that it's a kind of universal language rather than physical theory, which is compatible with all kinds of observation we may possibly obtain, you see? So it's not a physical theory which can be falsified or even verified, you see? It's rather a language. And in that sense, we need something as really physical principles rather than another piece of fancy mathematics for making advance in physics. No, okay, I think a physicist may probably tell more than I on these matters, but I think it's rather obvious that it's still very, very important topic. Okay. And I just wanted to mention one kind of funny argument against mathematical physics, right? Because one arguments are not funny, they're like this, right? That mathematics simply somehow helps physics, but it's not all physics, roughly. And as I say, historically, that sort of arguments, they go back to Aristotle.
Sorry, mathematical physics, you mean mathematical based physics?
I think, yeah, I think now, no, I think I used it rather in different sense as a kind of mathematically loaded physics. Well, that's I wanted to say. But you see, even Newton's title, of course, is a great book in physics, but I think his intention was really doing mathematical physics in that sense that you just mentioned, right? To provide mathematical principles. If we, at least if we believe Newton, that he really does what, no, say, we believe that he wants to do what he says he wants to do, okay? So he wants to provide mathematical principle of physics. So develop, yes, mathematical physics in this sense. But still, there is a lot of empirical content in that. So I don't know. But you are right, we should somehow distinguish between what is called today mathematical physics, right? If we consider it as a part of mathematics somehow motivated by possible physics application, it's one thing, and it's different thing if we are talking, even things like string theory, right? However, I think, you see, it's not very clear because I think we may formulate this Lee Smolin's critique of string theory by saying that it is not physics, but mathematical physics rather as a part of mathematics. I think that's more or less correct interpretation of his argument as far as I can see. Okay. Well, okay, we may, I hope we'll come back to these things, but I just want to mention what I think was kind of funny, but still I think this deserves be taken seriously, because there was an opposition to Newton on the part of people who argued that mathematics makes physics incomprehensible, okay? And being comprehensible for them, it's not only a question of kind of laziness to learn mathematics, right? But for these people, it was also a matter of keeping the status of physics as, say, I may say, a liberal art, right? As a science which is developed not by technician or some sort of specialist, by real gentlemen, you see, by free gentlemen who talk about these issues and just talking about truth, about the world, about the same way they are talking, I don't know, about politics, about justice in society, and things like that. So they would say mathematics really makes physics into something, how say, professional, not in the sense of professor, right? Ну, я могу по-русски, профессия по-латыни, значит, призвание. Как-то можно еще по-английски призвание, profession сказать. But in the sense of some technical occupation, right, of a specialist, and they thought it would be bad for this epistemic status of physics as a science. And I think that's something interesting. I think it's no, of course we cannot just buy this argument, that would be absurd. However, I think there is a problem because if we really believe that science, unlike say religion or something, right, should be something in a sense obvious, something that does not rely on any sort of authority, right, that every one may somehow understand himself or herself, you see, by his or her own mind. And that, by the way, also was, I didn't talk, it's about broader subject, but about that time that we discussed Descartes, we didn't discuss Francis Bacon, who was kind of founder of this British empirical tradition, and who insisted very much on that status of science as something checkable. And of course, today, it's very difficult to maintain, I would say, right? Because we should more and more believe certain experts, and believing experts is like believing authority. And so I think there is a real issue here, right? That's making science in general kind of verifiable, not only for some small group of specialists, but I say verifiable for public, let's say. I think it's very important how to do that without compromising the rigor of science. It's I think nobody has a solution today, right? I don't know how it's done these days, but say when I studied physics in school, right, we did some small experiments, you know, electricity, mechanical, so we could not only believe the teacher but believe our own eyes. Probably it's still done in schools today, but all that, of course, it refers to 18th, 19th century physics at best, right? And how to do something like that of physics of say 20th century even. I don't know. If you may demonstrate a laser, right? But it's like magic object, a laser. You see it works, but you don't know how it's done. Or someone tell you, but you should believe. You can check it.
Sorry, did I understand correctly that they say that science should be obvious, mathematics makes physics too technical, and we don't like it, but we can't offer something instead of mathematics?
Yeah. So there is a nice paper. If you're interested, write me an email. I'll find you. Except it may be in French, not in English. Perhaps.
What's the point? They already know about Archimedes and etc., who create really complex mechanisms, which is kind of difficult to understand without knowledge.
No, there are two remarks. Yeah, it's a good question. Two remarks. No, first remark, then you have a mechanism. It still makes things easier. That was actually Descartes' hopes, right? That mechanism, it's, no, imagine you have some very complicated kind of mechanical clock, right? It's maybe complex, but you can still see, kind of see, right? You can analyze it to minor detail by your own eyes. So you kind of see what part of, this mechanism pushes another part. So if you, I would say, have enough time and effort, you can understand how it works. Maybe not fully understand, maybe you're right, because no, but still, it's easier with say mechanism than with electronic stuff like computer.
And what about the Earth is round, and you need to use some technical techniques to prove it, like Greek philosophers do. You can do it if you can't.
Yeah, that is discussed. Yeah, that's exactly comes to my second point. No, at least that's kind of computation of size of the Earth that I referred to, right? It didn't use a lot of techniques, right? So yeah, that's kind of discussed issue in among historians, and the question is whether anything like physical experiment was ever, say, done in this ancient Greek science. No, there are different views on this matter, but I think still what can be that everybody would agree on some obvious things, and still obvious things that mechanics, right, was not seen by Archimedes or anybody else as a kind of a tool for studying nature. You see, mechanics was rather understood as a kind of a technical trick for satisfying some human needs, like military or something. And by the way, sometimes also historical stress that point that they were theoretically prepared to make much more mechanism than they actually did. You see, so all so this civilization was not based on mechanism. So in terms of mechanism, they had will and stuff. So they did not systematically use mechanism, we would say, economically, right? And some people explain that by the fact that indeed this science, mathematics, was kind of detached from what we would today qualify application, in spite of, say, figures like Archimedes, who really produced. I don't know. I don't have a strong view on this issue myself, but I think that's why it's certainly true, right? That mechanism. We may say that Galileo uses mechanisms for establishing physical principles, right? And that's, we don't find anything like that. By the way, in this Newton's book, there is no mechanism either. He, in that sense, here he is more traditional. He talks about heavens, right? It applies all to astronomy, first of all. Even I should look again, and you should look into Principia and see if there are references to really mechanisms there. I'm not sure now. I'm not such an attentive reader of Principia. Yeah, however, that certainly was a kind of shift and new understanding that we could really develop and use this mechanism in science, you see, in physics. Of course, you may qualify like astrolabia, some simple stuff, as mechanism, but that was not so systematic, at least.
I have one more question about this argument about how do you say it? About mathematics makes physics more complicated. I think it's very subjective argument, because if today, for example, any university students knows about calculus and about stuff they did, and maybe even more, and for them it isn't this isn't stuff that you can talk about.
Yeah.
You can observe it like and talk about like a gentleman.
No, I basically I agree with what you're saying, but I think it's still interesting argument which somehow stresses important aspect, right? That science really needs this public recognition, and not only on the basis of authority or of I don't know, atomic bomb or whatever marvel science can do for other people, but also in terms of understanding, real understanding of its first principles. And you are right. I think mathematics, if you do it properly, is such a thing that really allows it, right? You're absolutely right. However, you may probably you're right. It's kind of historical, because if you look into this, not in Principia, but the book I mentioned earlier, Method of Fluxions, right? As I say, it's a mess. It's kind of, you know, kind of thing that really you can learn only from firsthand, probably, right? Kind of technique. There is no really system. You should. So that very much may look like a kind of obscure, I don't know, alchemistry or something. Yes. Yeah, okay. Look, probably I give up the idea to talk about Leibniz. And actually, I plan to make a talk and a colloquium on your department, probably I'll tell them. And in the remaining time, better. Leibniz is extremely interesting figure, extremely. So no, maybe just few words without even showing text, going to details. No, first of all, he's not primarily a mathematician, right? He's a, I don't know, philosopher and even how it's now called, politically exposed person, who, among other things, took part into foundations in Russian Academy of Science. No, not directly, but indirectly, because Peter the Great communicated with him. There are letters. He gave certain advices on Academy, and that was very important part of his thinking. By the way, he was one who really thought globally, so to speak, right? And that was not usual for his time. In a sense, that was still heritage of what is usually called Age of Enlightenment, right? So all the skepticism about enlightenment, which arose in the 19th and late in 20th century, still was not there. But he really was this person of enlightenment who thought about humanity somehow. He was very rare European intellectual of that time who seriously studied Chinese, for example, you see. And by the way, his thought about Russia was as a kind of bridge between Europe and China. And that was one reason of his interest in Russian Academy of Science. And he also thought about some trading. So really was a fascinating person who never actually had a professorship in mathematics. And but he has a sort of mentor who was Huygens. And he came to Paris. That was still, again, about the same time. I'm now afraid we may look to Wikipedia, because I say I'm not good. Just Leibniz. Why he came to Paris. Yeah. And he had actually his he did some also differential calculus. And there are some published papers on that. However, his main mathematical project was developing what he called analysis situs, right? In Latin, analysis of position, situs. And that's, I think, is indeed very interesting idea. Idea was to upgrade Cartesian Descartes analytic geometry. And the idea why it needs upgrade, Leibniz idea, was that it somehow bears on the notion of magnitudes. So roughly speaking, it's all about lengths or perhaps volumes, as we would say today. It's not exactly that. I already stressed how Descartes himself would think about that, right? However, he wanted some sort of calculus, so he very much valued the same idea of calculus, of symbolic calculus, right? But one that would be not about magnitudes, okay? Even if we think now about this magnitude geometrically, not arithmetically. However, it would somehow compute position, right? So one way to think about this is something like combinatorial topology. However, indeed, he didn't have these ideas. He didn't have idea of topology. Now it's certain. I already mentioned that not all his mathematical papers are published, still published. Now there is still ongoing project of publishing what remains to be published, and actually he didn't want to publish them deliberately. And one specific reason for this was that no, first he was turned out from French Academy of Science, so he wanted to become an academician. That didn't work for him. I think that's exactly his Paris year. I know that's already in. Yeah, I think it was something sometime in 50s or 17th century where he came to Paris. Yeah, in 72 he came to Paris first. Yeah, and then he met Christian Huygens, who was a member of French Academy, even he was not French himself. And no, okay, I will not mention a lot of things happened. He had a lot of, by the way, he made one of first, say, computers, which is still sitting in his museum in Hanover. I shamefully didn't see it, but I hope to visit and see it. So that story that I want just to outline in very few words now, that he wrote a letter for Huygens where he described his ideas about analysis situs. Sorry, and at the same time he had already ready a memoir also on that stuff. And actually Huygens turned him down. He said, no, it's kind of not really comprehensible. And now we have this letter published. And so we may say actually Huygens was at least partly right. I have these letters. Leibniz, Huygens, right. That's the letter. Is it visible?
Oh, I don't see anything.
Yeah, that's the letter. So you can read it now. It's an English translation, and indeed, it's no. He had some ideas. For example, you know this traditional notation, say for triangle ABC, right? And if you think about this, there is kind of syntax which is wired internally, right? Because if we denote triangle ABC, it's not just a name, it's not just a paper name, but we also know it's a part of syntax, right? That say A, B, and C are vertices, are points, and A, B, B, C, and C, A are sides, right? So you have already a lot of information somehow hidden in that name. And so basically he wanted to develop this idea and develop some sort of symbolic calculus which would allow to do geometry as a symbolic computation without drawing diagrams. Or you may draw them, but just for somehow for better understanding's sake, right? And that wouldn't be metrical, unlike, say, standard geometry, right? But at that point, so Huygens turned him down, and that's true. There is no kind of result. It's rather all interesting, but description of project. And then actually, until the end of his life, he tried to develop these ideas, but he never published anything. And as I say, a lot of that stuff still remains unpublished.
Leibniz didn't publish.
Leibniz didn't publish. After Huygens, turned him down, he really didn't want to publish. Yeah, he deliberately didn't publish. He was very influential, very famous as philosopher. He published a lot of books. He also published some other mathematical papers, say on maxima and minima, so on differential analysis. However, that stuff he never published again. And still he worked a lot. Probably it's fair to say that that was like his main mathematical project, at least, right? Because he had many other projects, non-mathematical. And that was also related to his general ideas about so-called universal characteristic, which is kind of symbolic calculus for everything in one letter. To a friend, he, for example, says, I want a calculus which would allow me compute answer to, say, kind of moral question, right? What is good and what is bad? I want a calculus that really allows me just give some sort of initial condition and calculate rather than making all kind of endless disputes. So that sort of idea. And perhaps this geometrical part was really in the core of it, right? So you see many things relate here, logic, mathematics, even calculus, and even morality, even ethics. Right. So nothing was published in his lifetime. Only his pupil, Christian Wolff, who, by the way, was teacher of Lomonosov at a certain point, and Lomonosov translated Wolff's physics into Russian. By the way, it's rather interesting, even linguistically. And so this Wolff also published kind of treaty of calculus, and he made very short remark of the sort. I actually have it in my slides. A very short remark to the fact that sort of calculus that I expose here, right? Basically, Descartes analytic geometry with some infinitesimal stuff. It's not all of it. There is also Leibniz also have idea of genius of that different kind of calculus, which is analysis sitters, and that was all. He does not elaborate. However, somehow it's very interesting socially, say, right, that idea inspired so many people. So many people believe that should be some new kind of calculus that we should develop. And for example, one person who was motivated by that was Euler, and that would be part of my talk on analysis sitters. Another person who probably more seriously was motivated was German Grassmann. If you know Grassmann calculus and that stuff, that was directly motivated by Leibniz. Grassmann, on the other hand, he could read that letter already, which was published in 1750s for actually some contingent reason, because they just, actually it was published in the context of this contest between Newtonians and Leibnizians, who invented what first. And I forgot the name, someone who was Leibnizian, he just published all his available to him, say not all, of course, correspondence, including this letter to Huygens, who was dead to that time. Okay, so that letter was published. So say until almost the end of 19th century, where there was already kind of project of publishing Leibniz's, heritage, his stuff on philosophy and on mathematics. When more was published, that was the only available document, say, on Leibniz analysis. But still, it's inspired so much, even without having really, how say, fair mathematical content. That's, I think, it's also very, very interesting case when someone had idea, kind of vision, really no really mathematical results, and even without clear communication via published papers, somehow it works out, right? And people get inspired and develop stuff. And of course, topology, no, at least if we're talking about I forgot the name, who invented the word topology, was also, so topology, of course, was also motivated by this. And already in very end of 19th century, Henri Poincaré chosen the same name, analysis situs, as that time already the name for, say, algebraic topology. Yeah, but that was basically unrelated to what Leibniz really wrote out. He didn't have these ideas, of course, but still he somehow motivated this. Yeah, I think yeah, just in a minute. That's my topology. Yeah, Listing. That person was Listing, who introduced the term topology, and in a sense introduced also the concept, maybe not the first one.
По-русски.
Листинг, листинг, и это, кстати, есть на русском языке. Это называется предварительное исследование по топологии. Она под редакцией такого сталинского философа-математика Кольмана, тоже можете, так сказать.
А вы сейчас что-то показываете?
Давайте сейчас я поделюсь, да. Вы еще не... Я вас не задерживаю, нет? Ну, можем тогда чуть-чуть. Сейчас я покажу. Одну секунду. Так. Stop share. Сейчас я... Угу. Тут все в аудитории пар... Does everybody speaks Russian, or there are English speakers?
Судя по тому, кто здесь есть, нету тут англоговорящих, все нормально.
Тогда я могу перейти на русский. Вот, смотрите. Ну, ее, собственно, оригинал я как тоже скачал, он тоже доступен. По-моему, она отличная книжка. Вот первое издание 1948 года в Геттингене. Вот. А это, собственно, русский перевод. И тут как бы такая, это, понимаете, да, что это не теоретико-множественная топология, не общая топология, которой тогда не было, конечно, в это время, а скорее то, что мы сегодня назвали комбинаторной топологией. Так, сейчас там про Ленина, про Про то, как топология важна для народного хозяйства. Ну, кстати, да. Да, но при этом, понимаете, у него хорошего определения, что такое топология, вот нету, по-моему. Вот сейчас я тут. Да, но видите, вот при этом он тоже как-то возводит себя к Лейбницу, хотя вот кроме этого письма, в котором, ну, вы вот можете почитать, там, собственно, какой топологии нет, там все метрическое, хотя и Лейбниц хочет с этим бороться. Но вот этого, видите, как-то достаточно, оказывается. Вот, то есть, собственно, топологии там нет. Здесь, конечно, это самое, что ни на есть топология, но вот когда он, вот, говорит, следовательно, под топологией будем понимать учение о модаль. Я проверял немецкий текст, там вот действительно модальность почему-то. Будем понимать учение о модальностях, отношения пространственных образов, законах связан. Ну, то есть какая-то такая все-таки мутная, я бы сказал. Почему-то слово модальность, вот оно скорее из логики. Почему он решил его здесь использовать? У меня, например, нет объяснения. Ну, может быть, там какую-то литературу, если поднять, которую он читал, может, что-то можно такое найти. Взаимного положения, следования. Ну, вот это как раз традиционно то, что и Лейбниц сам говорил, ну, собственно, в этом письме, и то, что за ним там многие повторяли. Взаимного положения.
Может быть, модальное в смысле какое-то дискретное имеете в виду? Ну, как бы, ну, в том плане, что...
Ну, как бы, да.
Ну, что нас не интересует расстояние, там, нас интересует там слева или справа, ну, в таком смысле, как бы,
Ну,
я не
да,
знаю.
да. Ну, часто, знаете, в этом контексте вот употребляли разные люди слово «качественное». То есть количественное – это вот, значит, про
Да.
величины, а здесь вот как бы качественное. Ну, вот да, он модальный пишет. Что-то такое. Да. Посредством понятия следовательно. Вот, но, понимаете, идея, что это вот инвариант непрерывного, так сказать, преобразования, тут тоже нету на самом деле. Я не знаю, вот должны ли мы сегодня читать, вот может даже вы как-то сказать, математики тоже мне скажете, должны ли мы считать это, ну, вот таким определением, что ли, того, что такое топология, да, что это вот какая-то модальность, инвариант там непрерывных преобразований. То есть мы должны иметь вот это понятие о непрерывном преобразовании, чтобы говорить о топологии. Вот. У него здесь нет, это тоже явно.
А это какой год?
Это вот 48-й, 1800 в смысле.
Угу.
Там вот слово топология он раньше, по-моему, там в 60-х годах где-то еще в письмах каких-то употреблял. Но вот, видимо, публично он его, так сказать, тут делал. Потому что вот это слово, значит, был такой еще фон Штаут, у него книжка называется «Геометрия дер Лаге». Это, ну, какой-то начало, можете проверить, начало 19 века, ну, вообще, в случае, раньше. И ему вот это не нравится, геометрия дер Лаге, потому что вот, мол, слово вот геометрия, ну, кстати, оно не от Лейбница идет, да, ну, вот так сказать, на измерение нас сразу, так сказать, указывают, а вроде тут вот он не хочет указывать на измерение. Поэтому вот он придумал, собственно, из двух греческих корней составил. Ну, кстати, это так же, как, например, слово «телефон» тоже состоит, да, из греческих корней. То есть греческие неологизмы – это такая распространенная в этом смысле штука. Вот. Вот. И если мы будем вот такое считать определение с непрерывным преобразованием, то только это вот у Кляйна уже, да, Феликса Кляйна в ирландской программе, это, по-моему, 72-й год, 1872. И то там у него как-то это тоже, так сказать, мутновато сформулировано. Он там пишет о этих самых, как бы инфинитизимальных как раз преобразованиях. Но, по-видимому, надо иметь в виду, что они непрерывные. То есть он думает о чем-то вот типа там, я не знаю, группли, что ли. Хотя такого понятия у него тоже еще не было. Вот. Но, может быть, не надо, конечно, так вот ограниченно понимать топологию. Может быть, можно и шире. Но, во всяком случае, вот мои французские коллеги, которые вот Лейбницем занимаются, они как раз говорят, что ну никак там топологию нельзя найти у него, поскольку там все метрическое. Ну, понимаете, здесь же опять тоже вот такой вопрос. Если мы вот в старые тексты что-то такое вот современное вчитываем, ну, в общем, это такая процедура очень-очень плохо определенная, да? Хотя не всегда бессмысленная. Вот у того же Штаута, например, есть вот действительно топологическое доказательство вот про Эйлерову характеристику там, многогранника, да, потому что у Эйлера там чисто метрическое доказательство. И вообще Эйлер вот эту задачу о кенигсбергских мостах, значит, он связывает с этим анализом ситус, а вот эту задачу про многогранники, да, сколько там, чего, ну, то, что вот мы Эйлеровой характеристикой называем, там он вообще это не связывает ни с какой анализ ситус, то есть, ну, вот просто отдельно об этом пишет, и все доказательства чисто метрические там у него.
Простите, а может, пора перерыв уже?
Да, ну, наверное, мы заканчиваем тогда. Подождите. Сейчас я немножко со временем... Да, у нас же одна пара, и пора нам заканчивать, правильно?
Да.
Да, ну, хорошо. Вот. Так что нет, ну, пожалуйста, если какие-то вопросы еще кто-то мне сейчас... Может, про работу еще что-то или что-то я могу как раз обсудить.
Ну, про работу вот я прислал, если вам удобнее. Там...
Да, ну давайте сейчас обсудим прямо, давайте. Сейчас я выключу тогда